Okay. Good evening, everyone. Okay. Last time we've learned about the basic idea of duality in linear programming, which includes the economic interpretation of dualities. Okay, and we've considered this symmetric primal dual pair, right, to describe some properties of primal dual pair. And in this symmetric primal dual pair, the primal problem is a minimization problem with greater than equal constraint and the non-negativity restrictions, right? And the dual problem is the maximization problem with less than equal constraint with non-negativity restrictions, right? And if the primal LP is n by n, which means it has m number of constraints, of course not including the non-negativity restriction, and n number of variables, for example, then the dual LP must have n constraints and m number of variables. Is that right? Which means for every variable in the primal problem, there is a corresponding inequality constraints in the dual problem. Likewise, for each inequality constraint, not including non-negativity restrictions, there is a corresponding dual variables. Okay? And the right-hand side vector, the primal problem, serves as the objective coefficient vector in the dual problem. And the objective coefficient, the primal problem, serves as the right-hand side vectors, the dual problem, right? And this A superscript T represents the A transpose matrix, right? And A is here. And let's go back to the computer screen. We've also noticed if we have an inequality reversed in the primal problem in symmetric primal dual pair, in dual problem we have the reverse direction of the corresponding variable, right? And we've also noticed equality of the constraint in the primal problem corresponds to the unrestricted ensign of the variable in the dual problem, right? And last time we've also learned that the dual of the dual problem is the primal problem, which implies that given a symmetric primal dual pair of LP problems is arbitrary, which is referred to the primal problem and which is referred to the dual problem, right? So it really doesn't matter. In this case, the minimization problem is the primal problem and maximization problem is the dual problem. But it could be vice versa, okay? It really doesn't matter. Which means, for some cases, minimization problem could be dual problem. The maximization problem could be the primal problem, okay? And we've also learned that the dual problem can be directly defined from the primal problem. That is, the dual of an LP may be found by first rewriting the LP in the form of one of the LPs in the symmetric primal dual pair. And then use this table, we can construct the dual problem, right? And the last thing that we have learned during the last time is about the weak duality theorem. Okay? So if we reconsider the symmetric primal dual pair, then the weak duality theorem tells us that the objective value of minimization problem is always greater than or equal to the objective function value of maximization problem. Of course, in the symmetric primal dual pair. Okay? That is the weak duality theorem. Okay, then today we are going to learn about other duality theorems. First, the fundamental duality theorem. This theorem tells us, first, if both problems, the primal and dual problems, are feasible, and then both have an optimal solution, and their optimal values are equal. Okay? And second, if one of the problems, either the primal or dual, has an unbounded objective, then the other problem is infeasible. Okay? Third, if only one of the problems is feasible, then its objective must be unbounded over the feasible reason. Okay? And lastly, asks, okay, is it possible that both primal and dual problems are infeasible? Do you think so? Actually, the answer is yes. And I'm going to show you all of these 4 cases with an example. Okay? Okay, let's consider the first example. So from this example, we will say that if both primal and dual problems are feasible, then both have an optimal solution, and their optimal values are equal. Okay? So first, you are required to construct. So first, you are going to construct the dual problem and then demonstrate graphically both problems are feasible and both have an optimal solution whose optimal values is equal. Okay, so this example will show the first property of the fundamental duality theorem, right? Okay, so this is the primal problem. Okay? Change the pen. And this primal problem has 2 constraints, right? So which means the dual problem must have 2 decision variables. So if I say y variable is the dual variable, then the dual problem must be the maximization problem, of course. Okay. And dual problem has two decision variable, which is, let's say, y1 and y2. Okay? And because the primal problem has two decision variable, which means the dual problem must have two constraints, right? Let me write down. Okay, this is better. So we will have two constraints in dual problem, right? And the right-hand side value in the primal problem is 6, 8. So the transpose of this value must be the objective coefficient, which is 6, 8, right? And the objective coefficient is 20, 10, which means the right-hand side value in the dual problem should be the transpose of this vector, which is 20 and 10, right? And the constraint coefficient matrix in the primal problem is 5, 1, 2, 2, right? Which is A. So A transpose matrix, which is 5, 2, 1, 2, becomes the constraint coefficient in the dual problem, right? So 5, 2, 1, 2, like this way, right? And this given LP problem, the primal LP problem, is in the form of the primer in the symmetric primal dual pair, right? Which is, this primal problem is the minimization problem with greater than equal constraint and non-negativity restrictions, which is, has the same form of primal problem, the symmetrical primal dual pair, right? Which means the dual problem must be the maximization problem with less than equal constraint with non-negativity restrictions. So all the constraint should be less than equal sign, right? And both variable y1 and y2 should be greater than equal to 0. So we've constructed the dual problem like this, right? Okay, now let's try to solve the primal problem graphically, because it has only two decision variables. So graphical method does work very well, right? Horizontal axis is x1, vertical axis is x2, right? And let's say this is 4, 4, and is that 1, 6, right? Okay, maybe 1. Maybe somewhere up here we have 6. Down here we have 1. So, oops, this is 1. Okay, something like that, right? And because the origin 0, 0 does not satisfy both constraints, right? So we may conclude that the origin is not one of the feasible points, right? So the feasible region would be the points of above the line and the line itself, right? The feasible region would be something like this, right? These are the feasible region. Is that right? And the feasible region does include 1, 2, 3 extreme points, right? And another 3. This and this and this is the infeasible but basic solution, right? So total, in this system we have 6 basic solutions, and 3 of them is feasible and 3 of them is infeasible, right? I just want you to recall your memory. And to find the optimal solution, we need to graph a line on which all the points have the same z-value, right? The line is called the isovalue line, right? And to draw an isovalue line, we need to choose any point in the feasible region, okay? And calculate its z-value. So for example, if I choose the value 4, 0, okay? With 4, 0, the objective function value becomes 80, right? 20 times 4 plus 10 times 0 becomes 80. So we may say the point 4, 0 lies on the isovalue line. G equals 20x1 plus 10x2 equals 80, right? So we're writing this as x2 equals negative 2x1 plus 8, right? This is the isovalue line, okay? Which means this line has a slope of negative 2 and the x2 intercept of 8, right? So the isovalue line would be something like this, okay? And we need to move isovalue line either this direction or this direction, right? And actually in this problem, the objective function value, z, will be improved, which means the objective function value will be decreased because we are dealing with minimization problem. If we move in a direction for which both x1 and x2 decrease, is that right? Which means we need to move the isovalue line this direction, right? To obtain the optimal solution. And we know that this point is the optimal point, okay? Where the isovalue line intersecting the feasible region, okay? And actually this value is 0.5 and this value, y value is 3.5 actually. So x1 equals 0.5 and x2 equals 3.5 with objective function value is 45. Okay, this is the optimal solution with optimal objective function value of 45. Okay. Okay, now let's consider the dual problem. Okay. So the dual problem, the vertical axis is the y2 and the horizontal axis is y1, right? So it's like 5, 10, and something like 4 and 10. Those are two constraints. Okay. Let's change the color. And in dual problem, again, the origin 0, 0 does satisfy both of these constraints, right? So we may say that the origin is one of the feasible points. So the feasible region would be the point below the line and the line itself, right? So these are the feasible region for dual problem, which includes 4 extreme points, right? And in that case, the isovalue line would be something like this, okay? And the problem, in this problem, the objective function value will be improved if we increase both y1 and y2 values, right? Which means we need to move the isovalue line in this direction. There is the northeast direction, right? Which means this point is the optimal point, okay? Because the isovalue line touching the feasible region, okay? And this point is x1, x2 equals, y1 and y2, right? 2.5, 3.75, okay? And if I say the objective function value is equal to w, for example, then the w becomes 45, okay? So in that case, where is the primal? Primal objective function value, optimal objective function value is 45, and your optimal objective function value is again 45, right? So we have shown that this example have an optimal solution, and those two values are exactly the same, okay? Let's do R. Okay, now I'm going to show you that one of the problem, either the primal or dual has an unbounded objective, then the other problem is infeasible, which is the second case of fundamental duality theorem. Okay? What is this? So that is the example number 2. So first, we are going to demonstrate graphically this problem has an unbounded objective function, and then construct the dual problem and then demonstrate again graphically the dual problem has no feasible solution. Okay? Okay, so again, vertical axis is x2 and horizontal axis is x1, right? And the first constraint is x2 or let me say negative 2x2 first constraint is x1 minus 2 less than equals 2x2, right? So x2 is greater than equals half x1 minus 1, right? So something like this, negative 1 and is 2, right? And another one is x2 is less than equals x1 plus 4, right? So let's say this is 4. Right? Is that correct? And because the origin does satisfy both constraints, we may say that the origin is one of the feasible points, right? It should be, so the feasible origin would be like this. Okay. Which includes 1, 2, and 3 extreme points. And in this case, the isovalue line is something like this. Okay? Okay? Those are the isovalue lines. And in this problem, the objective function value will be improved if both x1 and x2 increase. Is that right? So the isovalue line should be moved this way. Is that correct? Is that right? because we are dealing with minimization problem. The improved means the objective function value will be decreased, right? So if we increase both x1 and x2, then our objective function value will be decreased, right? Which is improved. So the objective function will continue to improve the further away from the origin, right, into the unbounded region. So the primal problem has the unbounded objective. Okay? Now, let's construct the dual problem based on this primal problem. Okay? We immediately notice that the dual will be a maximization problem, right? And the size of the problem will be 2 by 2, because the primal problem has 2 constraints and 2 decision variables, right? Which means dual problem also have 2 decision variables and 2 constraints. So again, let's use y variable for the dual problem. So we have 2 decision variable and 2 constraint. Okay. And currently the objective coefficient is -1, -3, right? If I say this is the C, then the C transpose, which is -1, -3, becomes the right-hand side value, the dual problem. So -1, -3 here. The right-hand side value, the primal problem is 2, 4, which means the transpose of this vector becomes the objective coefficient, which is 2, 4, right? And the constraint coefficient in the primal problem, A, is 2 by 2 matrix, 1, -1, -2, 1, right? So a transpose matrix, which is 1, -2, -1, and 1, becomes the constraint coefficient in the dual problem, right? So 1, -1, -2, and 1, right? Now we need to determine the right direction for each constraint and the sign of each variable, right? Last time we've learned how to use this table to determine those signs, right? Okay, because in the primal problem, which is minimization problem, the first variable is greater than equal sign, right? So in the minimization problem, the first variable is greater than equal sign, which means in the maximization problem, the first constraint should be less than equal sign, right? So first constraint is less than equal. Likewise, in minimization problem, the second variable is greater than equal. Again, in the minimization problem, the first variable is greater than equal sign, which implies that in maximization problem, the second constraint should be less than equal sign. Okay? And in the minimization problem, the first constraint is less than equal sign. The minimization problem, the first constraint is less than equal sign, right? Which implies that in maximization problem, the first variable must be less than equal sign. Okay? Which is y1 is less than equal to 0. Okay? Likewise, in the minimization problem, the second constraint is less than equal sign, right? So in the minimization problem, second constraint is less than equal sign, right? Which implies that the maximization problem, corresponding variable, which is second variable, must be less than equal sign. So y2 is less than equal to 0. So this is the dual problem. Okay? Now, let's solve the dual problem using graphical method. Okay? Horizontal axis is y1, and vertical axis is y2. So, right? And two constraints would be something like this. Okay? And because the origin does not satisfy both constraints, which means that the origin is not one of the feasible points, right? So the feasible region would be this side and this side. So, right? And y1 is less than equal to 0. Likewise, y2 is less than equal to 0. So, should be something like this. Okay? So maybe something like this. The feasible reason would be not the feasible reason. Okay? So which means the two constraints are never in agreement in the 1, 2, 3 third quadrant, right? Which is y1 is less than equal to 0 and y2 is less than equal to 0. So this problem has no feasible reason. Is that right? Which means that this dual problem has no feasible solution. Okay? So this is infeasible. So this second example shows if one of the problem is unbounded objective, then the other problem is infeasible. Okay? Okay, next, I'm going to show you if the primal problem has no feasible solution, then the dual problem has an unbounded objective. Okay? This is example number 3. And this example, first, I'm going to demonstrate this problem has no feasible solution using graphical method, and then construct the dual problem and demonstrate graphically the dual problem has an unbounded objective. Okay? x2 and x1 axis, right? And the two constraints would be something like this, okay? And because the origin does not satisfy the first constraint, right? So the feasible region would be this side. Okay? However, the origin does satisfy the second constraint, right? Because 0 is less than or equal to 4, which means the feasible region would be this side. Okay? Because of the non-negativity restriction for each decision variable, we have feasible direction like this way. Okay? So again, we know that the feasible region is empty in this case, which means it contains no points, right? Since no points satisfy all the constraints, there is no feasible region. So it is an infeasible LP, right? So this is infeasible. So we have a primal LP which is infeasible. Okay? Okay, now let's try to construct dual LP. Again, we can see that the dual problem is 2 by 2 minimization problem, right? So y1, y2, and we have two constraints, right? Because the right-hand side value is negative 2, 4, objective coefficient becomes negative 2, 4. Objective coefficient in primal problem is 1, 2. So the right-hand side value in dual problem becomes 1, 2, right? And constraint coefficient would be negative 1, 1, 4, 1, right? And because this given LP, the primal problem is the form of the dual problem, the symmetric primal dual pair. Right? So its dual problem must be a minimization problem with greater than equal constraints and non-negativity restrictions. Oops, it should be 1. Is that right? So this is the dual problem. Is that big enough? Everybody can see this clearly? Okay. And in graphically, y2 axis and y1 axis, like this, right? And two constraints would be something like this, okay? And because the origin does not satisfy both constraints, because 0 is not greater than or equal to some positive values, right? So the origin is not one of the feasible points, okay? Which means the feasible region would be this side and this side. And because of the non-negativity restriction of each decision variable, the feasible region would be this side. Which means we have the feasible region like this. Okay? Is that right? And actually, the isovalue line would be something like this. Okay? Okay? And in this problem, we are dealing with minimization problem again, right? So the objective function value will be improved, which means the objective function value will be decreased if y1 increase, right? But y2 decrease. Is that right? So we need to move the isovalue line this direction. Is that right? So again, the objective function value will continue to improve. Is that right? It's not that clear, maybe? Is that clear? Our feasible region is this, right? So the objective function value will improve, continue to improve the further, again, away from the origin into the unbounded region, right? Is that right? So this is the unbounded case. So in this example, we've shown that if the primal problem is infeasible, then the dual problem has an unbounded objective.
Yeah. About the objective function, I don't know if the line is about the objective function, because I think that the slope is negative.
It's negative.
And the slope is positive.
I'm sorry? Y1 should be increased, right?
Yeah.
So it should, this direction, Y2 should be decreased, right? So the isovalue line should be moved in this direction, right? Okay. Okay. And now I'm going to show you that both primal and dual problems can be infeasible. Okay? So let's consider the example number 4. And like it says, first I'm going to demonstrate this problem. The primal problem has no feasible solution graphically, And then construct the dual problem, and again demonstrate graphically the dual problem also has no feasible solution. Okay? Okay, so in this case, something like this. Okay? And again, the origin does not satisfy both constraints, right? Which means the feasible region would be this direction and this direction, right? Because of the non-negativity restriction for both decision variable, feasible region would be this direction. Okay? So again, in this case, the feasible region contains no points, right? Because no points satisfy all the constraints. It is an infeasible. Okay? Now let's try to construct the dual problem. Okay? Again, because the primal problem is minimization problem, and it has only two decision variable and two constraints, the dual problem must be the maximization problem with two decision variable and two constraints, right? So let's again use y variable for dual decision variable. Sorry. Okay? Because the right-hand side value in the primal problem is 1, 1, becomes the objective coefficient in the dual problem, right? And the objective coefficient in primal problem is -1 and -1, becomes the right-hand side values in the dual problem. And the transpose of constraint coefficient becomes the constraint coefficient in the dual problem. So it's going to be 1, -1, -1, 1. It's the same, right? Okay? And because this given LP, the primal problem, is in the form of primal in the symmetric primal dual pair, the dual problem must be maximization problem with less than equal constraints, right? And of course, we should have non-negativity restriction. If you want to use the table, then because in the minimization problem, the first and second constraints are greater than equal sign, right? So in the minimization problem, first and second constraints are greater than equal sign, which implies that in the maximization problem, the first and second variable must be greater than equal sign, right? So we have both y1 and y2 is greater than equal sign. And in the minimization problem, both variable is greater than equal sign, right? The minimization problem, both x1 and x2 variable is greater than equal sign, which implies that in the maximization problem, the corresponding constraints, both constraints should be less than equal sign. So we have less than equal sign in dual constraints. Okay? So this is the corresponding dual problem. Okay? Okay, now I'm going to show you that this dual problem is also invisible using graphical method. Y2 and Y1, right? Again, our constraint looks like this. And the origin does not satisfy both of these constraints, right? Because 0 is now less than or equal to -1, which means the feasible region would be this direction. And the non-negativity restriction tells us the feasible region would be this direction, right? So again, the feasible region contains no points, right? And because no points satisfy all the points, all the constraints, it is an infeasible LP, right? So this example, we've shown that it's also possible that both primal and dual problems are infeasible. Okay? So I want you to remember those 4 possible cases. Okay? Okay, then next, let's talk about the complementary slackness theorem, which is another very important theorem in duality. So suppose x hat and y hat are the feasible solutions in the primal and dual problems, respectively. Then this x hat and y hat are each optimal in their respective problems. If and only if, whenever a constraint of one problem is slack, then the corresponding variable of the other problem is 0. And the complementary slackness theorem tells us whenever a variable of one problem is positive, then the corresponding constraint of the other problem is tight, which is binding constraint, right? Okay, now I have the example. Okay. Okay, so this is the complementary slackness theorem, right? And I want you to recall your memory that the primal and the dual problems are closely related each other, so that the optimal solution of one problem automatically provides the optimal solution to the other problem, right? And the next example problem will show how it does work. And we are going to use the complementary Slackness theorem to show that. Okay? Okay, so in this problem, again, first we are going to construct the dual problem and then find its optimal solution. And then use the complementary Slackness theorem, the optimal solution for the dual problem, to find the optimal solution for the primal problem. Okay? Okay, so the primal problem is maximization problem, and it has only one constraint. So the dual problem must be minimization problem, right? And it must have only one decision variable, right? The primal problem has two decision variables, which means the dual problem must have two constraints, right? The objective coefficient is 2, -4, which becomes the right-hand side value, the dual problem. And the right-hand side value is 1, so the objective coefficient becomes 1. The constraint coefficient is 1, -1. The transpose of that vector becomes the constraint coefficient, the dual problem. So it's going to be 1 and -1, right? And in the maximization problem, the constraint is less than equal sign, right? The maximization problem, we have a less than equal constraint, right? Which implies in the minimization problem, we will have greater than equal sign for the variable. So y1 should be greater than equal to 0, right? And in the maximization problem, both variables are greater than equal sign, right? The maximization problem, both variables are greater than equal sign, which implies in the minimization problem, both constraints should be greater than equal sign, right? So both constraints should be greater than equal sign here. So this is the dual problem. Okay? What is that? Okay. Okay, now we are required to find the optimal solution for the dual problem, right? So this dual objective function value will be improved, which means the dual objective function value will be decreased because we are dealing with minimization problem, right? If y1 variable is decreased, is that correct? And from the dual constraints with non-negativity restriction, we know that the lower bound of y1 is 2. Is that right? So y1 equals 2 is the optimal basic feasible solution. Right? Because y1 equals 2 does satisfy all of these constraints. Is that correct? And the corresponding objective function value is 2, right? So if I say dual objective function value is equal to W, then W is 2, right? Is that correct? And by the complementary slackness theorem, it does say whenever a constraint of one problem is slack, which means whenever a constraint of one problem is not tight constraint, then the corresponding variable of the other problem is 0. So, at the dual optimal point, which is y1 equals 2, the second dual constraint is not binding constraint. Is that correct? What about the first one? Is binding constraint, right? So this is not our concern. So I said at the optimal point y1 equals 2, the second constraint is non-binding, right? Which implies that the corresponding second primal variable is 0, which means x2 equals 0. Okay? And the complementary slackness theorem tells us whenever a variable of one problem is positive, then the corresponding constraint of the other problem is tight or binding constraint, right? So at the dual optimal point, y1 equals 2, the dual variable, which is y1, right, has a positive value. Is that correct? It's obviously y1 is positive, right? Which means the corresponding primal constraint has an equality sign. Is that right? So what is the primal constraint? Okay. Which means this constraint is actually equal to 1. Is that right? So y1 minus y2 equal to 0, right? If you use y2 equals 0, then what is the value of x1? Is 0? Or, hold on a second. It should be 1, right? Okay. So from here, x1 becomes 1, right? So with x1 equals 1, x2 equals 0. x1 equals 1 and x2 equals 0. The objective function value, the primal problem, becomes 2, right? Is that correct? So we've obtained the primal objective function value using the complementary slackness theorem. Okay? And actually, this result satisfies the weak duality theorem. What is weak duality theorem? The objective function value of minimization problem, in our case, which is 2, is always greater than or equal to the objective function value of maximization problem in the symmetric primal dual pair, right? So in our case, it does satisfy weak duality theorem. Is that correct? And also, this result satisfies the fundamental duality theorem too. So in that case, the case number 1, right? Because both a problem has the optimal solution and the optimal values are equal. Okay? Any questions? Okay, then this is all for today. And next time, I will give you more examples about the complementary slackness theorem. And then I'm going to introduce the dual simplex method, or maybe revised simplex method. Let me think about that, okay? Okay, thank you. I will see you next time. Bye.